Thank you for the introduction. Hello, everyone. Thank you for being virtually here today and for attending this year's VR conference. My name is Hakim Si Mohammed. I am a postdoctoral researcher at INRIA Rennes in France, and today I'm going to present to you the result of a work that was conducted in the scope of a collaboration between INRIA and the Technical University of Graz. This work is entitled Detecting System Errors in Virtual Reality Using EEG, which stands for electroencephalography, through error-related potential. In short, a very interesting property of the human brain is that when users witnesses or when they experience an error during the interaction, a very specific brain pattern happens in the frontocentral region of the brain that can be noticed in the EEG data, which basically looks like that. This signal is known as the error-related potential, aka the oh shit signal. Since it was first discovered in the early 90s, the error potentials have mainly been used in the context of brain-computer interfaces. Brain-computer interfaces are systems that enable to control or to interact with a system directly using the brain activity. And these systems are known to be very error-prone, and thanks to error-related potentials, it is possible to detect automatically when the outcome of the system is erroneous so that it can be corrected. The same applies also for the HCI community, who have seen in these error potentials an opportunity to create an automatic undo feature of the Control Z button with the idea of automatically canceling the last command sent by the user if an ERP is detected directly from the brain. But in VR as well, these ERPs have hold great promise, and the first applications have studied the interaction errors, whether they do generate error potentials or not. For example, a work by Yasmir and al where they implemented a system consisting in moving a blue dot, a blue ball here from the right to the left of the screen using a haptic arm, and sometimes the ball would just follow a straight line, but sometimes it would just appear after being occluded by the cylinder on a different height, which is perceived as an error by the users and do elicit error potentials. In the same time, Pedrao et al. Have studied error potentials as a neurophysiological correlate of state of agency, where they have demonstrated that when violated, the sense of agency between a user and its virtual avatar do trigger error potentials. So they use this pattern as an indicator of the violations of the state of agency. More recently, Pizzetta and al. Also demonstrated that observing errors happening during the interaction in VR also trigger error potentials. Despite these promising applications, the current state of the art of using ERPs in VR still holds some limitations. In particular, we know that several different types of errors can elicit these ERPs in the EEG data of the users. But yet, no previous work has tried to characterize the system errors happening in VR, or how do the users behave when the errors originate from the system and not from the users. In addition, we have noticed that in several cases, these ERPs were used as metrics of the user experience in VR regarding the state of agency or other parameters. But no previous work has tackled the possibility of the real-time detection of ERPs on the fly, detecting ERPs as soon as they happen. Considering these limitations, our work has focused on two research questions. First, do system errors, again, meaning errors generated by the system and not by the user, do system errors in VR elicit error-related potentials? And then, can we automatically detect these ERPs in VR? In order to answer these questions, we have designed an experiment where the main task consisted in a center out pick and place task where the user had to move a virtual object appearing on the center of the table to one of the shapes. The virtual table was mapped with a real one where the user could put their hands. There were three types of objects possible to manipulate: a tetrahedra, a cylinder, and a parallelepiped. And each one corresponding to a specific shape. Obviously, the tetrahedra goes the triangle, the cylinder goes to the circle, and so on. We designed four experimental conditions corresponding to the errors that we wanted to study in VR. The first condition was the correct trials, where basically everything goes fine. The user grabs an object and drops it into the correct shape. In this time, he or she gets a green feedback or positive feedback saying that okay, the correct shape, the correct object was dropped in the correct shape. The first type of error that we studied is the tracking errors. This corresponds to the situation where the object being manipulated by the user loses the tracking, or the system loses the tracking of the object being manipulated by the system. This corresponds to a situation where the object gets detached from the user hand and gets frozen in mid-air. In this condition, in this situation, we ask the user to remain still and not to go back to the object in order to remove or to reduce potential muscle artifacts. And in this case, no feedback is given and the user just has to wait for the object to disappear. The second type of error is known as the feedback error or the outcome error. They correspond to the situations where the outcome or feedback provided by the VR system does not correspond to what the user is expecting. Basically, in this case, the user still grabs the object, puts it into the correct shape, but gets a negative or red feedback from the system. The last type of error is the background anomalies. We wanted to see what is the effect of unrealistic and unrelated to the task rendering errors provoke on the user's brain. In this case, we have implemented it under the form of a frame put on the table that sometimes during the background anomalies, it would flip and be put in an unrealistic shape crossing the table. The rest of the trial goes unchanged. In general, our experiment consisted in 10 runs of 39 trials. Each run was consisting in 27 correct trials and 12 erroneous trials, divided between 5 tracking errors, 5 feedback errors, and 2 background anomalies. In total, we kept the number of error trials as a third of the total number of trials, roughly. And the general trial design starts when the object appears on the table, then the user grabs the object. In the case of the tracking error or the background anomaly, randomly between 25% and 75% of the total distance between the origin of the object and the shape, the error would happen. The object would be frozen or the frame would be flipped. In the case of the correct trial or the feedback trials, then it's only about the feedback that is provided when the task is completed that would change between positive and negative. Regarding the participants and the parties of the systems, 15 people took part in our experiment, 7 female and 8 males. They were all equipped with an HTC Vive virtual reality headset and a ANT Neuro EEG Ego Sport with 64 electrodes EEG headset. One difficulty regarding this experiment was to combine these two headsets together in a way that the pressure applied by the VR headset would not disrupt the EEG signal. The data collected was mainly the EEG data with a sampling frequency of 512 Hz. Regarding the results now, um, the results of analyzing the tracking errors versus the correct trials condition showed that the tracking errors did generate a strong pattern of ERPs, where basically we can see a strong negativity and then 2 peaks corresponding, which is very characteristics of the ERPs. And you can see that the main activity on the top plots here of the averaged activity of all the users, that there is a significant activity in the fronto-central region of the brain, while the correct trials remain pretty much still, which shows basically, these results show basically that there is a clear ERP pattern that happens after the error onset. Regarding the results of analyzing the feedback errors, we noticed that there was a slight negativity happening right after the erroneous feedback, but still a positive rebound happening in both of the positive and negative feedback. And it was quite difficult to really significantly disentangle between these two feedbacks. One of the reasons may be that the user actually maybe did not pay attention to the color of the feedback provided, as some of them reported going back to the center of the table before even noticing the feedback. Or it could also be because the task was so simple that the impact of the error itself was not strong enough, and the user were still convinced that they were correct despite the system giving a false answer. But yet, this will still need to be further investigated. Now, regarding the results of analyzing the background anomaly, the Doppler plots and the grand average brain activity of the users did not seem to generate any specific pattern when sorry, when the background anomaly happened, suggesting that either the users did not notice the happening of the error or maybe did not have any impact on them. But anyway, this kind of system error did not seem to generate any error potential. Regarding now the second question, research question of this paper about the single trial classification, our objective was to classify or to be able to classify each single trial into correct or erroneous trial, especially in the case of the tracking errors and the feedback errors. For doing so, we have considered 250 milliseconds long epochs or pieces of EEG data starting right after the event onset. The event onset corresponds to either the error happening or the same virtual time as when the error happens in the correct trial. As feature vectors, we considered the amplitude of the frontal-central electrode, FCZ, as it was the one that holds the most information on it and where actually the activity happens. And we trained linear discriminant analysis LDA classifiers in order to classify the trials. The results showed a pretty high classification accuracy for tracking errors with an average accuracy of 85% and almost 90% of TNR, true negative rate, which suggests a pretty high sensitivity and specificity, encouraging the fact that it is still possible to detect them in single trial, which is the first step towards their automatic detection. And regarding now the feedback errors classification, however, we could not detect significantly above chance level, or we could not classify with significant accuracy the trials between correct and erroneous feedback. But as we say, this may have different reasons that we still have to further investigate. Regarding now the results or the answer to the research question 1, do system errors in VR trigger error-related potentials? Our results indicate stronger ERPs generated by tracking errors. So the short answer would be yes, at least for the tracking errors, which were the most impactful, we could see clear generated ERPs. But background anomalies, for example, did not seem to generate any ERP. And now regarding the second research question about the automatic detection of error potentials in VR, we could notice that the tracking errors could be classified with high accuracy, but it was more difficult to classify between correct and erroneous feedback, and with results mostly below significant chance level. However, interestingly, we could notice that for 5 of the participants who could still classify between correct feedback and erroneous feedback with a above chance level accuracy, which is encouraging but still needs to be further studied. A last point of discussion was that in this work we did not try specifically to remove muscle artifacts. We just tried to separate the trials and only keep those with only keep those who looked clean, statistically clean. As a conclusion, as a summary of this work, we have conducted a user study to investigate the presence of ERPs when facing different system errors in VR. In particular, what happened when users faced tracking errors, feedback errors, and background anomalies. And the results suggest that the tracking errors in particular generated strong and classifiable ERPs, paving the way to new applications using the automatic detection of tracking errors in VR. Regarding this future work, our goal is later to design a technique for the automatic and asynchronous detection of ERPs. As we said, this was a first step when we demonstrated that the single trial classification of these ERPs was possible in VR, but we still use the information about when the error happens. The next step would be to design techniques that would allow to classify these ERPs on the go in real time as soon as they happen. And then this would also open the way for new applications of detecting ERPs in VR, like the automatic flagging of the system in order to be able to later review what were the events that maybe breaks the presence in VR thanks to the elicitation of ERPs that would be detected automatically. Well, this concludes my talk. I would like again to thank you all for your attention and thanks all of my co-authors for their help in realizing this work. And if you have any questions, I am ready to answer. Thank you.